So our third speaker today in this summary meeting on applicable resurgent asymptotics is Karen Yeats of Waterloo University in Ontario, where she holds a chair called the Canada Research Chair in Combinatorics and Quantum Field Theory. She worked previously at Simon Fraser University and before that with Dirk Kreimer at Boston University, and her title is Partial Combinatorial Interpretations of a Transseries Expansion. Over to you, Karen.
All right. Let me know if I'm not getting through okay, because I seem to be having a few bandwidth problems today.
It would be nice to see your face. We can only see your forehead at present.
Yes, well, I don't think I can accomplish that because I'm writing on the same machine that I'm drawing on the same machine that has the video camera.
Okay, okay.
But we'll see. I can do a little more there. Improvement, slight improvement. Okay. So I'm going to tell you a story, and a certain amount of it is somebody else's story, but I'm going to tell you some nice combinatorial things. And I'm going to start in the middle of this story with some numbers, because I really like sequences and when they count things. And there are some nice sequences here that count things. So up here along the top, what do we see? We see some numbers that count rooted connected chord diagrams. And so what do I mean by that? Well, I can make a chord diagram, looks like this. So I can make one with 2 chords. There's 4 ways I can make one with 3 chords. And if you're very bored, you can try to make the one with 27 chords. And go with, sorry, you can try to make the ones with 4 chords. Oh, sorry, I'm not quite, even though it's already been up for a while, I'm obviously not quite awake. You can try to make the 27 different ones with 4 chords. All right, going the other way, there's another sequence here that you might recognize. And what is this one counting? This one is counting labeled rooted trees. And it doesn't look so obvious because it's counting them exponentially. So when I see 3/2 here, I should really think of that as 9 over 3 factorial. And when I see this -1, well, I'm going to ignore the signs for a moment. I want to think of that as 2 over 2 factorial. Okay, and then this is 1 over 1 factorial, and this is 1 over 0 factorial, and so on. So what do I want to find? I want to find, say, 2 trees on 2 vertices, and they're labeled trees, so I can do that. Let's change color here. I can put vertex 1 at the top and then vertex 2, or vertex 2 and then vertex 1. Well, there's only one way to make a tree with 1 vertex, and there's one way to make an empty tree, which we'll call epsilon. And there's 9 ways to make a labeled tree on 3 vertices. I can have the I can have all 6 permutations of this guy, but when I try to make this guy, there's only 3 permutations because these aren't rooted trees with a plane structure. And so if I wrote 1, 3, 2, that would be the same tree as 1, 2, 3. And so 6 plus 3 together gives me 9, and sure enough, we get what we expect. So if you're coming at this from a discrete math perspective, this is looking like a lot of fun and something kind of exciting, because here we have this square of rational numbers. And when you go along the top, you get rooted connected chord diagrams. And when you go down the side, you get labeled rooted trees. And so there's a very natural question here of what interpolates, right? There should be some kind of object here that we can understand all the middle coefficients and that are counted by 2 parameters, and then limiting in one direction, we should get rooted connected chord diagrams, and in the other direction, we should get labeled rooted trees. Okay, and furthermore, this didn't just come out of nowhere. Borinsky and Dunne calculated or they obtained these guys and much more. It's easy to, the point is not that calculating the numbers, that's easy. The point is that they have a beautiful framework for doing these sorts of things. These are actually the rational parts of the coefficients in a particular Transseries expansion of a nice quantum field theory problem. Okay, so let's look at it. So we count some things. We saw the rooted connected chord diagrams. We saw the labeled rooted trees. But now let's see where this came from. And then let's think about how we can try to say something about some of the other things that are getting counted.
Karen, there was a question on chat. Do we need to bother about the minus signs, or are you going to explain them?
Well, the long answer is the minus signs are a big deal. And I will mention that a little bit at the very end. The short answer is they're what happens to come up in these expansions that I'm going to tell you the physical origin of in a moment. So they do matter. And your ultimate, if you're me and you want to have a combinatorial explanation, you do actually want to also account for the minus signs. Hopefully that's a sufficient answer for the moment. I will come back to it. And if I don't, you should ask again. I'm not sure if I see the chat. I surely must see it somewhere, but it doesn't, seems to have been misplaced. Anyway.
It's all right. I'm monitoring the chat for you. You don't need to bother about it.
Okay, perfect. So you'll let me know if other things show up. Okay, so where does this come from? This comes from something that David did with Durkheim some time ago now. And they considered a particular situation. And it was, I mean, a really nice example that an awful lot of my work has actually just come out of this one beautiful example that they worked on. So what kind of diagrams are we considering? We're considering diagrams, and they're just made of iterating this one Yukawa graph into itself, but it's still more than just chains or rainbows because I'm allowed to iterate it into itself in any kind of way. So I can, get something like this, whatever suits your fancy. You can put lots of them in. But it's just made with that one loop graph. Okay, and you can write down a Dyson-Schwinger equation that describes this situation. And for once, I've actually written it in close to their notation instead of, I usually write it in a different notation that because I'm weird. Oh, the tilde went to the wrong place. It should be here. Okay, so you're trying to compute these the corrections to this guy, to this propagator, and so that's this thing. And then you say, okay, but I know how to do that because I have the overall loop integral and I have a recursive insertion of the same thing, and that'll give me this. And I want to renormalize by subtraction, so I want to have the same integrand evaluated at some reference scale, and we usually use this, or they use this q squared equals mu squared, and that's also what I have been using since because it's a good way to do it. All right, so this is something that they solved in a very nice paper from 2000, and there's sort of two or three, depending on how you want to think of it, steps. And I want to emphasize some of the combinatorial underpinnings, but I also do want to get you to the sequences. So we will actually look at the more analytic part as well. We need to get to the resurgence at some point. But first, let's just notice that the shape here where we say, okay, I've got something and then I'm inserting into it some geometric series of itself. Well, that's just the functional equation for the generating function of unlabeled plain rooted trees. So these are also rooted trees, but they're slightly different. Before we had labeled trees and they were not plain. What does plain mean? Plain means that you have an order structure at the vertices, and this is the Kramer-esque notation for the operation that adds a root to a forest of trees. So, I mean, what's going to happen here? You say, okay, well, you have your A is counting your vertices, and so you have some vertex that's representing the new root that you've added. And what do you add inside? Well, you add some sequence of other trees. And that's saying, what is a tree? Well, a tree is a non-empty tree is a root and some sequence and you have to sum over all the possible not the possible sizes, lengths of the sequence, and so that's where you get your geometric series. Okay, more interestingly, perhaps for you guys, they rewrite the Dyson-Schwinger equation, but turning it into a differential equation. Okay, and it looks something like that. And then they do some very beautiful and clever work. And I think this is one of David's specialties of doing these sorts of beautiful analyses. They at some point expand out the series and do some manipulations and recognize the complementary error function and see some very nice functional relations. And it's all very beautiful. And they also find what's going to be more important for today is something that actually doesn't need all of this work, only some of it. They find a very nice differential equation for the anomalous dimension. And yeah, I've slightly written the wrong thing. I should, this is the differential equation for the anomalous dimension. And later I'm actually going to want to scale it by a half. And so my gamma 1 is not quite the right notation, but there's this nice differential equation. And I say it's nice, but notice there is some striking nonlinearities here. So it's nice, but it's not simple. Okay. Now there is mildly a more general framework here. If we start with something of a similar shape, so a different functional equation for trees, or a slight generalization for the functional equation for trees, this would be saying, okay, your generating series for your trees is made up of adding a root 2, and now you can, well, if you either have, you're inserting multiple different sequences of subtrees, or depending on the sign there, you're just inserting some fixed number, which could be empty, each of which could be empty. So you can build binary trees this way. If your exponent is 2, you clearly can build the example we had before when the exponent is -1, and everything else in that whole story. It's not all simple tree classes, it's only the ones in this shape. Okay, and then the analog here of this guy is what I would usually call G, and we want to expand it, and we want to look at these. We want to expand it in this scale parameter. It turns out that this thing is really only dependent on log q squared, and in fact, with the renormalization by subtraction, it's just log q squared over mu squared. So you can expand then in L, and you get these guys. The first one of these is up to a half, which I didn't deal with correctly on the previous page, the anomalous dimension. And furthermore, if you just write down the renormalization group equation, I mean, what is that? It's relating L derivative and an A derivative and just a sort of constant piece. And if you just extract coefficients in L, then the renormalization group equation becomes an equation here, and it's this equation here. So it's a nice recurrence for the gamma k in terms of the lower gammas. And so that story always works. Furthermore, you can always get some kind of a gamma 1 recursion, but it isn't always as nice as the one on the previous page. So this one is extra nice because the initial setup was extra nice. Still, you can do a similar game with more primitives, and you can do a similar game for systems of equations instead of just single Dyson-Schwinger equation. But okay, fine, you can do that. Okay, now back to the Yukawa setting, the initial Yukawa setting. David and Dirk also already knew that the anomalous dimension in this Yukawa setting is the generating series for rooted connected chord diagrams. Now it's time for me to actually define some things. So you probably guessed what's going on with the chord diagrams, but I think I want to make explicit a few things just so that we're all on the same page. So here's my chord diagram vocab. So first of all, what is a chord diagram? You want to think of it, if you have some points here on a circle, and I better draw an even number of them. I didn't really space those out very well, did I? Let's space those out slightly better. And then you put some chords. I mean, that's why it's called a chord diagram, right? There's a chord diagram. Now, what happens if it's rooted if it's rooted, that means you're identifying one of these vertices as special, and you're identifying an orientation. So normally you would expect to have at least a rotation symmetry, or probably a dihedral symmetry, depending on what you're doing exactly. But if you remove those symmetries, then you have a rooted chord diagram. And once you have a rooted chord diagram, you can redraw it in a linear format. Right, so I can say this is 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. And if you redraw it in the linear format, you get something like this. And so now you can say, what is a rooted chord diagram? Well, we can just say it's a matching on the set 1 up to 2n for some value of n. And n is the number of chords. The edges of the matching are the chords of the chord diagram. Connected is probably what you're imagining. So this is not connected because it's not connected. If you want to think of this more rigorously, you can build a graph called the intersection graph, where you take a vertex for each chord, and the vertices are adjacent if the chords cross, and then you're actually asking if that graph is connected or not. So that's all fine and good. And so that's what rooted connected chord diagrams are. And rooted connected chord diagrams, that was the top row of that first square. And it was already clear that this is also what you get from that gives the anomalous dimension, the expansion for the anomalous dimension in this Yukawa setting. Okay, this also sits inside a somewhat more general framework. And this slide is hideous because it's just full of equations. But what is the idea? The idea here is, okay, I want this GXL. It's supposed to solve the Dyson-Schwinger equation. This is a slightly different, there's a different way of writing it, which I'll come back to in a sense. So this really is the Dyson-Schwinger equation. And you can solve this with a sum over chord diagrams, where each chord diagram is contributing. This is just a monomial. So here's the definition of this. It's a product of binomial coefficients. The A is just a monomial in these lowercase a's. And then there's this extra little piece, but that's just a very small polynomial in L. So this is really quite well controlled. And what you should think is each chord diagram is just contributing a very small thing. And if you took the lowest coefficient of L, so you're taking the anomalous dimension, then there's only one term in this bracketed part. So you're really just getting a monomial. Each chord diagram is contributing a monomial. Furthermore, if you were in the Yukawa case, then you'd be in the situation that S equals 2 and that there's no sum over K, there's just K equals 1. So this is just the -1. This power would just be -1. And this sum would be gone, and you'd have K equals 1. And furthermore, your F here is just a geometric series. So when you expand it out, you're just like all of your AIs are just some constant. And so then when each chord diagram is just contributing a monomial and you've reduced away all of those things, then you're just counting the chord diagrams. And more generally, you get this messier stuff. You get, you need to not just have rooted connected chord diagrams that we had before, but you also need to put positive integer decorations on the chords. They're sort of like weights. And then you use that, that's the DC, you use that to build this product of binomial coefficients.
Karen, we've lost you.
I don't know, I'm sorry, I guess I have a bad network today. I was just about to explain what the heck this F is. And if you recall the situation that David studied with Dirk, there was only one Feynman diagram that everything was built by just iterating. And so somewhere you got to actually get the Feynman integral of that guy involved, and that's the F. And so in that case, there'd just be one F. These would all be constant. But in general, there will be many primitive diagrams, and you need their coefficients in order to get the full expansion. Okay, now this is not primarily what I want to talk about today. There are some more things that I haven't really explained, and maybe I will say just a few things about some of the language, but really I want to go on and talk about the work that Michi and Gerald did. So just to give you this little bit of the language here. So in this context, I want to sort of weight all these chords. So you could imagine that there's some very thick chord that is weighted with a 3, say. Just as an example, this would be a 3, and then maybe this one is weighted with a 1, and this one is weighted with the 1, and those are those decorations. The other thing that's important to know is what is a terminal chord. So, and a terminal chord is one, here's the chord, and there could be stuff coming out this way, that's totally fine, but there's not allowed to be anything like that. That makes it a terminal chord. And so if you go back here, you see we're treating the terminal chords and the non-terminal chords differently in terms of which coefficients they pull out. And I don't want to go into the exact details of what gets pulled out where, but just you look at the chord diagram and you can build its contribution in a much simpler way than building a Feynman integral. It's just, than doing the Feynman integral. Building the Feynman integral is okay. Okay, this is cool stuff, and I've been working on it for the last number of years now. And it's both nice combinatorially, and to some extent, I think it's rejuvenated the study of chord diagrams. And it is kind of nice physically too. It's particularly nice for studying leading log and next to leading log and that whole story, because that's, if you're constraining where the terminal chords are, and that constrains the shape of the diagram. Okay. But what I really want to say today needs another important piece. And these are the pieces that involve the asymptotic series. So, well, let's think about rooted connected chord diagrams. So I've been talking about their generating series, and let's now give it a name. For the moment, I'm going to call it C of X. So we got C of X. This is going to be the generating series for rooted connected chord diagrams. And let's let the coefficients be Cn. So we'll just write it as Cn x to the n. All right, and those are the first row of that first page. And there's a classical result that gives the asymptotics. And here's the first term. So just the first term in the asymptotics. And what do you get? You get a gamma. So there's clearly factorial growth here. There's a +1/2, and that's not too surprising. So you're seeing this sort of odd double factorial behavior going on. And then with the 2, you're seeing the odd double factorial going on. And then there's an E and some stuff like that. Okay, so this is a classical result due to Kleitman and also with Stein and Everett. But you can in fact get much more. And this is part of a framework, a very nice, more general framework for factorially divergent series that was developed by Michi Borinsky in his PhD thesis. And he looks at the rooted chord diagrams specifically as an example of his framework. So let's just think a little bit about that. So what is this framework? How does this work? So suppose you have a series, and you know the form of the asymptotics of it. So this is AN is supposed to have this form. So you have a gamma, you know what the shift on the gamma is, you know what the power part at the beginning is, and then you just have the coefficients of the expansion. Okay, and then Borinsky wants to define this particular thing. You take these coefficients and you put them together into a new series. So this is it's an alien derivative, and he uses this notation. And for rooted connected chord, and then it developed a lot of very nice theory about how this behaves, and you get lots of very nice theorems that let you actually do stuff. And in particular, for rooted connected chord diagrams, you see that the correct parameters are 2.5, and you get this formula. And that is essentially the second row from the first page. Now, if you're looking carefully, you'll see it's obviously not exactly the second row from the first page, because you're going to get a power of e, and you're got a root 2 pi. And so obviously it's not rational. But those, if you look slightly more carefully, you'll see that those are just an overall factor that comes out. And so I just scaled them away because I'm interested in the rational coefficients. Okay. Now, what can you do with this? And this is where Michi and Gerald, just last year, they gave this very beautiful resurgence analysis of this original Yukawa Dyson-Schwinger equation for that particular case that Dirk and David had studied back 20 years previous. And this is the same, a smaller version of the same table of numbers, now with their notation. So to show you that these are the rational parts of the expansions here. So what do you have? You have your C0 of x, that's the perturbative piece. Okay, you want to slightly scale it to make it line up exactly, fine. And then you have a 1 instanton piece, and it has, so it would be coming with an e to the -1 and this zeta, which this psi, which I will say later what it is, but that's the actual instanton factor. And I don't want those because I want to see the rational coefficient, so I just scaled them out, and so on. And a part of this story is very soon I'm going to start expanding the other way, and we'll see that that is a very interesting expansion as well. Okay, so how do they do this? So they start with the Dyson-Schwinger equation the same way we've all been starting. But it's worth pointing out what this means combinatorially, because the Dyson-Schwinger equation, well, let's begin with it at the level of the anomalous dimension. And we saw that pages and pages ago. All right, I promise I won't scroll back too many times because I know it can be mildly nauseating, but let's just scroll back once and let's look at this. It's written in a slightly different way, but look what we see. We see the gamma 1, we see the a d by dA of the gamma 1, we see the gamma 1 squared, we see just a, and we see another gamma 1. And well, here I've actually done, and I have an overall 1/2 away from where I was before, which is where I want to be. And you see this is actually the same equation. So this is the Dyson-Schwinger equation in an important way. It's the Dyson-Schwinger equation at the level of the anomalous dimension. And it's also combinatorially a classic recurrence for rooted connected chord diagrams. So let me explain to you how this works as a classic recurrence on rooted connected chord diagrams. So you're saying on this side, well, how can you make a rooted connected chord diagram? Well, we're going to consider, it could be just a root, okay? Or it could have some more stuff. And what is that more stuff going to look like? So if you remove the root, because it's connected, when you remove the root, you just get this sort of rainbow of pieces. So we think of these as the connected components after you remove the root. Okay. And so now what am I going to do? I'm going to break these into two sort of parts. So one part, ooh, I'm not going to break them with that thick of a line, am I? Oh, sorry. Okay, I will just break them this way then. So one of the parts, you could take, say, this part, and then the rest, we'll take all the rest together, even though there's more than one connected component. No, I did it the wrong way. Sorry, one more time. Let's do this one more time. I'm going to take, first, I'm going to take everything but one of the components, and I'm going to keep the root with that. And the other thing I'm going to do is take just one of the connected components. Okay, so the part that still has the root, what is that going to look like? Well, I'll just put it here So there's all this part, that part, and that's corresponding to this C of X. But now the other guy, there's something special going on because it's not just a rooted connected chord diagram, it also has a marked interval. And that's what this is doing. So when I say X, that's like marking a chord. Sorry, when I say, when I take the derivative, that's like marking a chord. And I haven't changed what I'm counting by, so I have to multiply by X. So that's X divided by dx, that's your pointing. But now each interval, there's 2 intervals for each chord, except I certainly couldn't do the last interval. And so I get exactly this equation, 2x d by dx of the chord diagrams minus once over to take out that last interval. That gives me chord diagrams with a marked interval. And that's exactly what I need to put together to build the chord diagram. Okay, so now what? They have this equation, however you want to think about obtaining it. And then they use this Transseries ansatz, you plug it in. And now let's think about taking coefficients of different powers of sigma. If you take the coefficient of sigma 0, you just get this same coefficient, same formula, right? And so you solve that and you get the generating function of rooted connected chord diagrams, surprise, surprise, because there it is. And that's your perturbative part, which we already knew was essentially rooted connected chord diagrams. Okay, well then let's take the coefficient of sigma to the 1. That's, if you just look up there, you think, well, what am I going to get? I'm going to get C0s and C1s and their derivatives mixed in a way that's not too complicated, but I didn't want to write it down because the slide is already kind of full. But you get a really nice explicit equation. You can manipulate a little bit using some of the facts that you know, and you solve it, they solve it, and this gives you the 1 instanton part, and so on. You get the 2 instanton part from the sigma 2, and so on. Okay. But these expressions, and this is where if you go back to the work from Mishi's thesis, you see that this isn't just to sort of grind the calculation. There's actually a nice sort of, you get particularly nice expressions that are very structured, and they're sufficiently structured that you can actually write down the whole thing. So you get this simple, fairly simple all orders expression. And here I finally told you what psi is, and there you see, look, there's the actual instanton behavior that you were expecting. I'm sorry, I should have written that sooner. So it turns out that you can just think of, you take this little expression, this f of xy, which is, you know, built out of the kinds of pieces we've been looking at, and some y derivatives, and then you build that operator and then ultimately sub in the C0, the connected chord diagrams for y, and that gives you the whole C of x. And furthermore, and this finally to get back to the square, you can expand the other way. Okay, the correct variable for the other way is this rho variable. You sort of think, well, really it should be psi, but you have to do a little bit of shifting to make it exactly the right thing. And now you can play exactly the same game, right? I have this expansion, and I can think about, oh, why did I write? No, that's right. Surely this has got to be a row. Sorry about that. Anyway, you think about, no. Sorry, never mind. Don't let me second guess myself. You expand the other way and take the different coefficients. And so for the F0, just directly from the Dyson-Schwinger equation, you get this equation. And similarly, a more complicated for the higher FIs. But now some of you guys are special functions people, and you will immediately know what this is. It's something that's built out of the Lambert W function. And so this is what you actually get. The F0 is just 1 plus Lambert W. For those of you who aren't special functions people, here is the definition of Lambert W. But this again has a combinatorial meaning. And Gerald and Mishi knew this. I mean, this is not my contribution by any means, but it's in fact classical that Lambert W is essentially giving you the generating series of the labeled rooted trees. So what do we need? Here's how you show this. first of all, you want to work with exponential generating series. So that means you're dividing each object by the factorial of its size. So in this case, size is number of vertices, which is what we saw right there on the very first page. And then, well, what do you say? Well, a non-empty, I'm not going to write it in words, I'm going to draw a picture. So if you have a non-empty rooted tree, well, what is it? I can actually draw almost the same picture, right? It's a root attached to a forest of subtrees. But here you don't have an order structure, but you do have to worry about labels. And so what does that end up meaning? That means that R of Z, well, I have to have a Z for the root. And then I say, okay, how can I take a set of labeled objects, an arbitrary set of labeled objects? Well, you actually know this as physicists. It's the same as how you go from arbitrary Feynman, from connected Feynman diagrams to arbitrary Feynman diagrams. It's exp. So you get that guy. That's the functional equation for the exponential generating series of labeled rooted trees. Okay, but then rewriting that, you can see, I mean, what is that saying? So rewriting, that just says R of Z, e to the minus R of Z equals Z. Okay, that's basically the Lambert guy. There's just a sign difference. So R of Z is just minus Lambert W of minus Z. Okay, and so F0, that first term, is just labeled rooted trees. And now you start to see, this is the first hint of where the sign is coming in. And so you have labeled rooted trees, but they're going to be counted by -1 to their size. Well, -1 to their size plus 1, there's an offset. And so that's the kind of sign that I figure in an ultimate goal of a combinatorial interpretation, that's okay. It's like, yeah, there is a sign, you got to put it in, but it's under control. It's just counting something very sensible in the object. Okay. So if you were noticing the section headings, we started in the middle and we did the beginning, and you'd think we'd do the end, but we don't really do the end because, in fact, I can't actually prove very much, which maybe explains why I spent a lot of time talking about things that either a few of them I had proved but are old, and most of them, the exciting ones, are ones that other people had proved. But I still want to tell you a little bit about something that we can do. So this is work with Ali Mahmoud, who was my PhD student. He graduated and he spent the last year at a postdoc at University of Ottawa. And okay, this is some of what we did together and some of what he did for his thesis. So we had this expression. So this, remember, was the expression for, if you want to think of it as the first instanton expansion, or you want to think of it as the asymptotic series for the rooted connected chord diagrams, or whatever it is. And we had that Stein recurrence for the rooted connected chord diagrams themselves. We can use that to get rid of this derivative. This is really then just exactly the same equation rewritten that way. And well, I just want to pull out that overall factor with the 1/e and the root 2 pi. And so let's just pull that out, right? So there's the e to cancel it off. And I'm just going to just literally get rid of that root 2 pi. And so I'm now interested in working with this guy. And this guy is literally the coefficients of, or they're literally the second row on the first page. So here they are. And you can look at them and you can be like, okay, those are not too crazy, right? And what am I seeing? I am seeing some signs. Okay. I'm seeing some powers of 2. I'm seeing some other things, so probably some factorials or something like that sneaking in there. But the denominators are not too crazy. And the numbers, well, I don't know what they are, but they don't look too crazy. But we can't do it. And I'll explain a little bit at the end about why it's so hard, and why some of you guys are probably sitting there and thinking, well, of course you can't do that. And I will address that at the end. So let's start even smaller and just think about the part in the argument to exp, at this part. Okay, and I don't want, there's an overall sort of denominator of 2. I don't want that, so let's just multiply it all by 2. and I'm actually going to get rid of the constant term as well. And so then I get this sequence. Okay. I'm going to go back and phrase it in terms of using the Stein recurrence. I'm going to rephrase it this way, because this you can give a combinatorial explanation as an exercise, basically. This is the sort of thing I could ask in a fourth year enumeration course. In fact, what is this? This is rooted chord diagrams with at most 2 connected components. And I'm going to just explain to you why it's that. So remember, we already said that when I took, well, there's an x, it should be an x d by dx. Sorry, there's an x missing here. We already said that when I take 2x d by dx of the chord diagrams, that's marking an interval. So if we think of our chord diagram here, we got some example chord diagram, and we're marking all these intervals. And when I subtract off the c of x, then that was sort of subtracting off this last interval. It wasn't there. Okay, that was for 2. And that would give us all connected chord diagrams using the Stein recurrence when I have this extra guy out here. Remember, because I said, okay, well, what am I going to do? I'm going to go and I'm going to take it and I'm going to put that one diagram inside the other diagram at the marked interval, and that's the Stein recurrence. That would be the 2x minus c of x. Now I've got 2x c prime of x minus c of x. I've got 2 more x c prime of x's. So that means I have to take each interval and I have to have one more thing that I can do with it. Okay, well, what am I going to do with it? I'm going to put another chord diagram. Just put the chord diagram there. So if you want to insert in the blue thing, you just literally put the chord diagram there. So let's say I have this. Oh, my color scheme is not consistent. I have a bad color scheme. Okay, so let's say I have this guy. And what am I going to do? I'm just going to literally put this guy in there. Okay. And I'm perfectly allowed to just literally put another guy at the end. That's fine. It's another connected component. Whereas this operation, I can't just do at the end. In fact, if I do it at the end, it just gives me the same result as subbing something underneath. And so this is rooted chord diagrams with at most 2 connected components. Okay, that's kind of nice. But that's kind of textbook. But it turns out now you go look this up in the OEIS, which of course is what you do with a sequence. I mean, you did that long ago, right? You did that on the first page when you're like, I don't like this talk. I'm going to look all these up on the OEIS. And this is what it says. And you think, that's not a very nice description. These numbers are the coefficient of x to the n. The nth one is the coefficient of x to the n in the generating function to the power of n. Sorry, the coefficient of x to the n in the generating function of this sequence to the power of n is another sequence in the encyclopedia. And that other sequence counts indecomposable chord diagrams. I didn't say what indecomposable is. I have to tell you now. Indecomposable means you're not allowed to do this. That's not allowed. That's not indecomposable. But it is perfectly okay to do that. So they don't have to be connected, but you couldn't break them apart with like a vertical line. They're not a concatenation of 2 chord diagrams, is a good way to say it. And so what I'm going to finish by telling you about is this is calling for an explanation, right? We've got the chord diagrams with 2 components, or most 2 components, and they're related in this kind of interesting way to indecomposable chord diagrams. So that's got to have a nice bijective proof, and it does. That we can do. You might object that the way we write it isn't fully bijective because we do use Lagrange inversion. And that's kind of expected, because this sort of thing where you take a coefficient of x to the n in some generating series to the nth power, that's exactly what shows up in Lagrange inversion. So Lagrange inversion is a series, a way of expressing the functional inverse of a series in terms of all the series that are in play. It does have purely combinatorial proofs, and it's also very useful in enumeration. Anyway, because of that, the actual bijection isn't literally between the 2 objects I just said. Because another way of thinking, a way of combinatorially thinking about Lagrange inversion is that you have a tree structure. because composition of generating series is essentially giving a structure of one object on another object. And so the key, what we end up with is a bijection between labeled ordered triples of a single chord and two rooted chord diagrams, and the set of rooted trees with vertices. The vertices could have multiple atoms in, and I'll show you a picture in a moment that'll make sense. And where the children of each vertex have the structure of a rooted tree chord diagram with at most two components. Okay, what the heck is that? Okay, you need an example, and here's the example. So this is an ordered triple of a chord and a chord diagram and a chord diagram, and we are in a labeled situation. And here, this is what I mean about you can have more than one atom inside, right? That's having more than one atom in that vertex. You've put the vertex is like a little path of three things. And what does it mean to have a chord diagram structure? It says along with these guys here, you don't just have them. You also, if you think of each of these as chords, you have the information of how they would link together as a chord diagram. Okay, that's a kind of esoteric object, but it's exactly what you want then to use the Lagrange inversion and get prove that this sequence really is the one that comes up in the OEIS. I was just going to show you the first step or so of this proof, of this bijection, because I think it's hard to see from here what the heck is going on. So what's going to happen? Well, we start, notice here, I think I will just use a few colors in the highlighter here. Here is the root, and that goes here. Okay, so we have a 2. Now, the next thing we do is we take the component that includes the root everywhere else. So this is the component that includes the root. And here, this is the component that includes the root. Okay, so if I go down here, let's write down the components that include the root. So we had this vertex. Oops, my color coding is getting messed up. We have this guy, which is the root of the tree. And now we want to take the components that include the root in the two chord diagrams. And so what do we have? We have this 11 and 1, and we have this 3, 7, 13. Okay, I don't know why the order got swapped. That's how Ali set it up. It ended up getting reversed at some stage. And those are building for you the children of the root. So you have an 11, you have a 1, you have a 3, you have a 7, you have a 13, and you keep the information of this chord diagram structure for those children. Okay, now you have to imagine putting each of these vertices or their corresponding chord into a queue, and you're going to process each one in turn. So the first one I would process is 11. And if you're bored, don't worry. 11 is also the last one I'm going to process, but the same idea will hold. So I go back up here and I say, okay, here's 11. And now what I want to care about with 11 is, you could imagine there's sort of two intervals that are determined by 11. There's the one that comes right after the beginning, and there's the one that comes right after the end. And now, right after the beginning, you get this chord diagram, and right after the end, you get nothing, because there's no chord diagrams in there. But there could, in general, be chord diagrams in both of those positions. And so those are the two pieces that you want to consider. And so if you think of this original triple, your triple is now the chord 11, the piece that was under it, and the piece that was beside it. Okay, well, it turns out that in that case, so now we're processing 11 with, this was 20 and 14 and 5, and then the third thing was just empty. Well, it turns out that in this case, there's only, because one of them is empty and this guy is only a single chord, that's the situation where you just grow this vertex. So this vertex gets an 11 and a 20 in it. And so that means we also now have to remember the 20 here. And you'll see that that's, no, sorry, that's a lie. I don't want to remember the 20 there. I want to remember the 20 associated with the 11. So just, so that's this chord here, let's double color it because it's now associated with 11 and 20. As it's associated with that vertex. Okay, and then you know that the children are the remaining guy. They're this 14 and 5. And so underneath this now big fat vertex that's made out of 2 dots, you have the 5 and the 14. And now you keep going. So next you look back in your queue and you'd process vertex 1. And it turns out when you process vertex 1, nothing happens. Because you look here at vertex 1 and there's nothing beside it and there's nothing after it. And so there's nothing to do. Similarly for 3. When you get to 7, there's stuff going on because 7 has something beside it. Oops, the 16. And so on. So it has something beside it and it has something under it and something beside it. It's got this big thing beside it. And so, not surprisingly, it's got lots of children and you do some stuff and things happen and you get this guy. So that's the bijection. Okay. I'm going to now, I said I was going to end at the middle and I'm going to literally end at the beginning because I want to go back to this table. So is this actually plausible that we'd be able to find a meaningful combinatorial interpretation for the whole thing? And now if you're on the side that says, no, Karen, you're being silly, your biggest argument is probably going to be the signs. And the signs are why it's not just an exercise. That first part was kind of an exercise, not that tree bijection. That was a quite pretty but non-trivial thing. But that very first step where we got to the connected chord diagrams with 2 components, it was sort of an exercise. And the reason it was an exercise is because when you manipulate the generating series in certain ways, you know what that does to the objects. But once you get signs, it's a little trickier. Because in general, if I want to subtract two generating series, if I want that to still have a nice combinatorial interpretation, I need to know not only have the subtraction in some abstract sense, but I actually need to know how I'm viewing these objects inside these objects so I can actually literally take them away. And because of this, because there's that sign, if you start, the next step would be to take the exp of the chord diagrams with at most 2 components. And in principle, I know what exp does. It takes labeled objects and it gives me the disconnected analog. And so I would be getting sets of chord diagrams with at most 2 components. But there's a sign. And so what that sign is telling you is that there's some cancellations. And if you want to get a combinatorial handle on those cancellations, you actually have to sort of know how the different sets sit inside each other. And so that's why it's not a triviality. And that's probably your biggest argument why it's a pipe tree. On the other hand, this situation is so beautiful and structured, right? This isn't just some arbitrary divergent series that happens to count something. It is a very nice thing that comes from a particular field theoretic context. The whole resurgent analysis, you can write down the all orders result in that very nice way. And you can then solve it the other direction and get these nice columns, which also are at least begin in a well-behaved way. So personally, I'm hopeful that this situation is nice enough that in fact there would be something more general to say, and I could answer my original question. And part of the reason I would really like that is I think it would tell you something about the physics here. I hope it would. You guys can answer that for me. And I think it would also, well, if you come from a formal series side of things and a combinatoric side of things, and you see these wonderful trans series, you say, something's got to be counted by that. And I think it would also give a really nice first example of something, whatever this common object is that could generalize to both, or that could specialize to both of these cases, this common object should be something that really has a trans series generating function, and that's the right way to count it. And I would love to see that discovered. So I'll stop there. Sorry about the technical issues. I'm not sure why I'm having a bad network today. And thank you very much for listening.
Thank you, Karen. So this talk is now open for questions. If I don't hear a question soon, then I have a comment to make. Dick and I are very, very happy that Karen has had such combinatoric pleasure on one of the 2 problems that we solved. 20 years ago. That's Yukawa theory in 4 dimensions, where the Dyson-Schwinger equation gives for the anomalous dimension only a first order differential equation with only quadratic nonlinearity. We also solved for phi cube theory in 6 dimensions, where we produced a third order differential equation with quartic nonlinearity with 3 instantons. And that has been studied very recently by Michael Borinsky, who's not here because he's on holiday, by Gerald Dunne, who's attending to family business in Australia, and by Max Meinig. And they have looked at the resurgence of that. And just last weekend, Mishi Borinsky and I arrived at an all orders conjecture for the structure of that resurgence. It involves logarithms, and we have an explicit conjecture involving 6 constants, you might call them Stokes constants, that completely describe the resurgence of that. It hasn't featured in Karen's talk because we don't yet know of any combinatorial significance of it, but it's a structure that is more refined than, say, Painlevé 1, and it beautifully fits in with the subject of this school. So
it's too bad that the relevant people are in various other things, and because I was actually sort of hoping or expecting almost that I'd hear a talk about that, and I think it's very beautiful from everything I've seen.
Well, people want an introduction to that, and it's beautifully written with many references covering physics and mathematics. Then on the archive, Borinsky, Dunne, and Meinig. It's a very scholarly paper, and it just begins to explore the resurgent structure, which Mishi and I think we conquered last weekend. So end of advertisement. Now, as I've taken up time, are there any comments or questions from other people? If not, please end the recording.